Hello, in this video we will study how to find surface area of a solid region formed by revolving a region about the x-axis or the y-axis. Okay, firstly, let me remind you about the formula how to find arc length of a curve, because we will use that formula and use the main idea for this problem. Okay, suppose we have this function y equal to f of x, and we need to find arc length of the graph of this function on the interval a and b. So the arc length is equal to integral from a to b square root of 1 plus f derivative of x squared dx. And let me remind you the main idea to obtain this formula, right? So the main idea of this is, you split a and b into small pieces. Okay, let's zoom this out, and then we approximate the arc length by the length of the straight line, by the distance between these two guys, just AI and AI plus 1. And then we sum them up, because we already split the interval a and b into small pieces, right? Then we sum them up, we consider some limit, and we get the formula. All right, now let's use this idea to find the surface area. Now let's say I will rotate this region. Let me clear this, and then we have some region in here. That is our region. Okay, I rotate this region about the x-axis. Okay, I will get some solid region. Okay, we know how to find volume of this solid region using the disk method, right? And now we want to find the surface area of this. All right, so let's do this. Again, I will consider some, small pieces in here. Okay, and then in order to find the surface area of each small piece, I need to approximate, the surface area of this guy by the surface area of the corresponding frustum. So the frustum look like this. Here's the frustum, right? Look like this. We cut that. So let me draw in another picture, right? So you have something like this, and this is our frustum. You see? Maybe the curve looks like this. The curve looks like this. The curve looks like this. And we approximate, the surface area of that piece by the surface area of the frustum. And we know the surface area of the frustum in this situation can be found by using the formula surface area I write here frustum equal to 2 pi r L, where L is the distance from this point to this point. Okay, you see where this is L. So basically L is what? L is the distance from here to here, from this point to this point. And we know the distance formula, right, between those points. And right there, that is what? That is 2 pi r square root of delta xi square plus delta yi square, right? Delta xi square plus delta I square. And what is r in this situation? What is r? The radius. So the radius I can write. Yeah, I can choose the midpoint in here. That is for some x, right? And the radius is just the function value. The radius is just the function value, right? So r in this situation is f of x. So I can write, yeah, that is equal to 2 pi f of xi, and here I have square root of delta xi square plus delta yi square. And we do the same trick for the arc length formula. Now we will pull delta I square out of this square root. We will get something like this. This is equal to 2 pi f of xi square root of 1 plus delta yi over delta xi square times delta xi. You see? And now we take sum, right? We sum them off. We get surface area of all frustums. So we get some sum in here, Riemann sum from 1 to n. 2 pi f of xi square root of 1 plus delta yi over delta xi square delta xi. And then we consider some limit when, delta xi, let's say the norm, which is, the maximum, let's say that. Because, sometimes we talk about this, sometimes we just say, yeah, we have all delta xi are the same, right? So everything is good. And when we consider this limit, we will get some definite integral. Integral from a to b, 2 pi, because 2 pi is just a number. I can bring this out of the integral. F of x without xi, sorry, just f of x, and then square root of 1 plus this guy, as we've seen in the video when we study arc length, right? This is just f derivative of x square and then dx. And that is the formula of the surface area. So now we will use this formula to solve a couple of problems, right? That is surface area. Remember that this is the formula of the surface area of the solid region when we rotate this region about the x-axis. So when you rotate that region about the y-axis, you would need another formula. Don't forget about that, okay? So let's consider the following example. Example 1. Let's consider the function f of x equal to x cubed, and on the interval 0 and 1, okay? And we rotate our region about the x-axis. So let's say, yeah, let's graph the function first. Here's x, here's y, here's 0. X equal to 1, y equal to 1 in here, okay? So here's 1, 1. And then the function should look like this. Yeah, that is our curve. And now we rotate the region about the x-axis. Let's rotate this about the x-axis. So we get something like this. So we get something like this. So I hope you can imagine, right? Something like this. Yes, and we need to find the surface area of this solid region. All right, now I will start from the beginning, right? So I will take some cutting here. Suppose that is x, and that is f of x, and that is the radius. So the radius again equal to f of x. Then we have surface area equal to 2 pi integral from 0 to 1 f of x, because the f of x is the radius, then square root of 1 plus f derivative of x squared dx, where f derivative of x is equal to 3x squared, because our function is x cubed, right? And now I substitute f of x and derivative of f into the formula. I get the surface area equal to 2 pi integral from 0 to 1 x cubed square root of 1 plus 3x square dx. That is 2 pi integral from 0 to 1 x cubed square root of 1 plus 9 x to the 4 dx. Now you see, this integral is very familiar to us. You know why? Because let's mention that we have x cubed and dx in this integral. And see, when you have something like that, right? You have x dx. Remember that the substitution is u equal to x squared. If you have x squared dx, the substitution is u equal to x cubed. If you have x to third dx, substitution u equal to x to the 4. You know, something like that, right? Of course, you can consider like linear combination, like in this example. So, based on this observation, I will put u equal to 1 plus 9 x to the 4. I put u equal to 1 plus 9 x to the 4, you know, it's just put the whole thing, right? Because the derivative of 1 is 0. So from here, I get du equal to 9 4 x cubed dx means 36 x cubed dx. We already have x cubed dx in here, you see? And now we can rewrite our integral in terms of u. But again, right, I will not write integration limits. I just need to find antiderivative of our function. Okay, so I write antiderivative of x cubed 1 plus 9x to the 4 dx equal to x cubed dx is du over 36. So if you divide both sides of this equation by 36, you will get x cubed dx is just du over 36. Okay, and then I have to write like this, right? Write 1 in here, and then square root of u du, because you already put u equal to this guy. Okay, and this integral is pretty easy. That is 136 u to 1/2 du, and you can use, you know, the power rule. It's just 1 over 36 u 1/2 plus 1 over 1/2 plus 1 plus c. Let's simplify that. Here 136 u 3/2, and here 3/2. Okay, plus c. So you flip 3/2, just, you know, multiply by 2 over 3. So I get 2 over 3 times 36 u 3/2 plus c, which is 1 over 3 times 18 u 3 over 2 plus c, and I write that is, you know, 54. And then I will not write u in this case. I will bring our substitution back here, because our substitution is what? Is 1 plus 9x to the 4. So I have 1 plus 9x to the 4, 3/2 plus c. All right, so only at this step I will plug integration limits, which is 0 and 1, right? So I have the area equal to 2 pi 1 over 54 1 plus 9x to the 4 3 over 2 evaluated from 0 to 1. And my job is just, you know, plug everything into this formula. I have pi over 27 because 2, we just simplify 2. And here I give 1 plus 9 times 1 to the 4, 3/2 minus 1 plus 9 times 0, 3/2. And then you can use calculator to find this number, right? Basically, that is pi over 27 and here 10, 3/2 minus 1. So that is how we can solve, we can solve the surface area problem. Okay. Before we move to the next problem, I would like to mention one thing. So at the beginning, I remind you about the arc length formula, right? So if you compare the arc length formula and the surface area formula, you see there is only difference in here. The difference is in here. This part is the same, right? But in the surface area formula, you have the radius. So don't forget about that. All right, let's move to the second example. Let's find surface area of the solid region obtained by revolving the region enclosed by the graph of 36 minus x squared about the x-axis on the interval -6 to 6, and right here about the x-axis. Okay, let's graph this function. Okay, so this function looks like this: x and y in here, -6 in here, and then 6 in here. When x equal to 0, that is 6 in here. So we have some kind of this. Okay, and this is our region, and we rotate this region about the x-axis. We get something like this. So I don't know if you can realize what is this. So actually this is a circle, right? So when you rotate this, you get a sphere. All right, so we need to find the surface area of this sphere, basically. Of course, we know that formula, right? But now we need to use integral to get that. So firstly, I need to find the derivative of this function, right? Let's find the derivative. So y prime is equal to, I write this function as 36 minus x squared to 1/2, right? And then I use the chain rule to differentiate this function. So the outside function is the power. I bring power down and have 36 minus x squared, and then 1/2 minus 1, and multiply by the derivative of the inside. The inside is 36 minus x squared. The derivative of inside is just -2x. Okay, let's simplify 2 and 2 in here. So I get -x, right, times 36 minus x squared, -1/2 in here. But again, since we have -1/2, we can flip that. We can rewrite in the form equal to -x over square root of 36 minus x squared. So this is our derivative. Okay, once we have the derivative, we just plug the derivative and the function into the formula, right? Here we don't have any problem with the radius, because the radius is again just equal to f of x, right? That is the radius. So let's plug everything into the formula. Where's the formula? Okay, so I can write the formula: surface area is equal to 2 pi integral from -6 to 6, right? F of x square root of 36 minus x squared. Inside I have square root of 1 minus y prime square, that is -x over 36 minus x squared, and then square dx. Let's simplify this integral. That is 2 pi from -6 to 6. In here I have square root of 36 minus x squared. Inside the square root I have 1 minus x squared over 36 minus x squared dx. All right, now inside the square root, I can simplify more. I will, cross multiply. So I have 36 minus x squared in here. Okay, minus x squared in here. So I have this is equal to, and then divide by 36 minus x squared. That's what happened inside the square root. Oh, no, sorry. I think I got the wrong formula in here. So actually, this should be plus, you see? So I feel something wrong in this. So this is plus. So this is plus. Okay? So if we have plus over there, so x squared minus x squared will be cancelled out. Perfect. We have very simple integral. 36 minus x squared, integral from -6 to 6, and then 2 pi in here, and then dx in here. All right, so now everything looks really good. 2 pi, -6, 36 minus x squared, and then I write really short, square root of 36 over square root of 36 minus x squared dx. And now we can simplify, this guy and this guy, the square root of 36 minus x squared. And square root of 36 is just 6, right? So I can rewrite our integral as 2 pi integral from -6 to 6 dx. So I hope we know how to do this, right? 2 pi times 6, and then, integral of -6 from -6 to 6 dx. And this integral is just equal to 6 minus -6, and which is, 12, right? So finally I get 2 pi times 6 times 12. And that is the final answer. The final answer is 144 pi. All right, so we already did 2 examples, so I hope that you understand how to solve this problem, right? Basically, if you don't rotate your region about some axis except x or y, so you need to take care about the radius. Otherwise, just go ahead to apply the formula of the surface area. And that formula is right here. It's right here, surface area formula. Okay, so I hope that you enjoyed the video, and I hope that this video is helpful for your study. Thank you for watching.